CCSCAL2 taught us one of the basic stuff about calculus, the concept of differentiation. We learned to get the derivative of a function using the definition, which takes a lot of time, and using a number of theorems, such as the power rule, the constant multiple rule, and the sum rule, to name a few. But did you know that we can get f of x given the f prime of x? This is precisely the reverse process of what we learned during CCSCAL1. Anti-differentiation is the inverse operation of differentiation. It is a process that leads into finding the antiderivative. Based on definition 4.1.1, any function f is called an antiderivative of the function f on an interval I of f prime of x is equal to f of x for every value of x in I. Too difficult? Let us use an example to interpret that definition. Say that function big F is as follows. F of x is equal to fx cubed plus x squared plus 5. From CCSCAL1, we learned that through constant multiple rule and sum rule, we can get the derivative. F prime of x is equal to 12x raised to the 2 plus 2x. If small f is the function defined by this derivative, then small f now becomes the derivative of big F. That just means that big F becomes the antiderivative of small f. But wait! Here's an interesting fact. Let's rewind a bit. Isn't it that when we get the antiderivative of the constant, we just drop it? It does not matter how big or small the value of the constant is, we just drop it. This is what is stated in Theorem 4.1.2. If f and g are two functions defined on an interval I such that f prime of x is equal to g prime of x for all x in I, then there is a constant k such that f of x is equal to g of x plus k for all x in I. Theorem 4.1.3 further states and formalizes the antiderivative concept. If f is a particular antiderivative of f on an interval I, then every antiderivative of f on I is given by f of x plus c, where c is an arbitrary constant. Anti-differentiation refers to finding all antiderivatives of a given function. This symbol denotes the operation of anti-differentiation. It was Leibniz who introduced this convention. We now write the derivative of f of x dx is equal to f of x plus c, where f prime of x is equal to f of x and d of f of x is equal to f of x dx. Notice that f of x plus c is the general antiderivative of f. Do not forget to add the constant of anti-differentiation. Let's get started. Let us discuss the techniques and properties in getting the antiderivative. The general formula for the antiderivative of dx is x plus c. Remember that the derivative of x is 1, and we call the power rule, where the derivative of x raised to n is the product of the exponent n times the value x raised to the exponent reduced by 1. We now apply the reverse process in anti-differentiation. The next property concerns values with exponents, such as the following: the derivative of x raised to m dx. In getting the derivative, we reduce the exponent by 1. In anti-differentiation, it's the other way around. And instead of putting it beside the base, The result is put as the denominator. Remember that m cannot be equal to -1. The third property is pretty much the same as that of our lesson in CCSCAL2 concerning constants in the given. In this expression, a is extracted outside to the left of the integral symbol, and the expression to the right of it is separately solved. Solving expressions involving sums in the antiderivative process is done by separating the expressions and finding the antiderivatives separately. The process is also the same when mixed together with constants. Let's now work on individual examples to apply the properties we learned. For our first one, let us find the antiderivative of 27dx. To solve this, let us extract out the constant outside to the left of the derivative symbol. Next, we find the antiderivative of dx. It is x plus c. We distribute 27 to x plus c, which we yield result to 27x plus 27c. We now conclude our answers to 27x plus k. Let's work on our second example. Let's find the derivative of 2x raised to the 7 dx. The property states that we increase the exponent by 1 and put it on the denominator of the expression, which yields the result of 2x raised to the 8 over 8 plus c. Simplifying, the final answer is 1 over 4x raised to the 8 plus c. For our third example, we find the antiderivative of x to the 4th times the quantity of 5 minus x squared dx. The first step to solve this problem is to distribute x raised to the 4th to 5 minus x squared. And then, we now increase the value of the exponent by 1 in each of the expressions. And include the constant of anti-differentiation. The final answer becomes x raised to the 5 minus x raised to the 7 over 7 plus c. Let's have some examples with fractional exponents. Let's find the antiderivative of 5u raised to 3 over 2 du. First step, we separate the constant to the value of u raised to 3 over 2 and increase 3 over 2 by 1. Notice that when we increase values of exponents, we automatically remove the derivative symbol right away. After simplifying, we get the answer 5 plus 2 over 5 u to the 5 over 2 plus c. The final answer now becomes 2u raised to 5 over 2 plus c. Now, let's have some examples with rational expressions on the denominator. In this case, let's see this example. Let's find the derivative of 3 over the square root of y dy. First, we extract the constant 3 to the left of the derivative symbol. For the next step, let us recall that the square root of x is equal to x raised to 1/2. With that being said, the expression now becomes 3 the derivative of 1 over y raised to 1/2 dy. Next, we now get the reciprocal of the expression so that the denominator now becomes the numerator. Getting the antiderivative, we will now add 1 to the value 1/2 negative on the numerator and the denominator. We now simplify it to 3 times 2y raised to 1/2 plus c. And then the final answer will be 6 square root of y plus c. You may also find these trigonometric antiderivatives helpful in your pursuit of study of CCSCAL2. Let's now get the antiderivative of a trigonometric function. Let's take this example for instance. Let's get the antiderivative of the quantity 3 sine t minus 2 cosine t dt. Using the formula we showed to you previously, the answer is negative 3 cosine t minus 2 sine t plus c. Let's find the antiderivative of sine x over cosine squared x dx. First step is we need to apply the lessons we learned from CCS trig. We separate cosine squared x into 2 expressions and our solution becomes this. Sine x over cosine x becomes tangent x and we multiply it by 1 over cosine x dx. One over cosine x becomes secant x, so that the expression now becomes the differential of tan x secant x dx. Simplifying, the answer is secant x plus c. That's it! Those were the basics of anti-differentiation. Congratulations! Hope you will have a wonderful time studying CCSCAL2. Till next time for more CCSCAL2 Primer.